In recent years, advances in biotechnology have generated signs of rapid development in the smart cell industry.
The cells of living organisms constantly produce new compounds through metabolism. The smart cell industry aims to rationally design cells from sources such as microorganisms and leverage their biological productivity. We can then create useful substances such as EPA that makes blood flow more smoothly. We use cutting-edge technology to design genomes, the blueprint of our cellular functions, and create cells that produce valuable substances. They're known as smart cells. They allow shorter product development cycles, improving production efficiency and volume.
Mr. President, I just saw the email.
Ah, then you know our health supplements are selling well.
Right, because they contain a lot of EPA.
But the price of fish, the raw material, is soaring.
How about producing EPA with smart cells?
Smart cells?
They visit a consulting firm specializing in the smart cell industry.
With the right cell engineering approach, we can make smart cells that produce EPA.
So how do you make them?
Allow me to demonstrate. Show us the DBTL cycle. The first step is to design a plan defining the optimum microorganisms to use and how to combine their genes to make smart cells that generate the desired substance. Then we build the smart cells according to the plan. We then perform tests to confirm that the productivity of the smart cells meets expectations. These test results provide feedback for future optimization. Then, when you want to increase productivity, you return to the basic design. We repeat the cycle of design, build, test, and learn to create smart cells that meet your needs and specifications.
I see.
Very rational.
Let's examine the process of making smart cells. First, the design phase.
First, we choose the microorganism that will become the matrix for the smart cell system. EPA belongs to the omega-3 fatty acid class of molecules. Yeasts are the best organisms to use to produce it. Let's see the list. Of all the available yeasts, I recommend this one because it produces a lot of oil.
Once the matrix microorganism is selected, we must think about how to combine the genes to produce EPA.
This is the genome of the oil-producing yeast. We will incorporate genes from an organism that produces EPA to re-engineer it as a biomanufacturing engine. In this case, the data indicates that algae genes would be suitable.
Algae have the capacity to produce EPA. Let's look at the metabolic pathways.
This is the map of the algae's metabolism. This area represents the EPA-producing pathway. And here is a map of the oil-producing yeast's metabolism.
So you'll insert the algae's EPA-producing genes here to transform the yeast?
Yes, Professor Shirai will show us how to carry out this recombination. Professor, where should we insert the genes?
They must be connected to the linoleic acid biosynthetic pathway. That will allow the yeast to produce EPA.
Understood.
Once the metabolic pathway of the cells is defined, enzymes are selected to enhance the reactions. The choice of enzyme greatly affects the quantity and quality of the substance produced by the cells.
Professor Araki, can you choose an enzyme that works well with this pathway? Certainly. For pathway A, this enzyme should work. And for pathway B, I would recommend this enzyme.
In this way, once the matrix microorganism, metabolic pathway, and enzyme are selected, the design of the SMART cell is complete.
Ms. Nakagawa, thank you.
I hope you'll approve the results.
The next step is to execute the plan and actually build the SMART cell. First, using specially designed robots, the genes related to the metabolic pathway as well as the enzymes are synthesized artificially. Then, using an automated system, the genes are inserted into the oil-producing yeast. This process creates SMART cells that produce EPA based on the oily yeast. Next, the efficiency of the SMART cells is assessed.
Mr. President, we just received the SMART cell prototype.
Good. Start testing as soon as possible.
These tests evaluate the prototype SMART cell platform for its ability to generate the needed substance in the right quantity and quality, with a view toward industrial-scale production.
Mr. President, here are the results.
It really is producing EPA.
How about the production?
Can you improve on these numbers for the sake of profitability?
Not to worry. Let's look at some ways to improve production.
Once we have the test results, we can interpret them and optimize the process.
Where should we start then?
In terms of overall metabolic balance, the activity of enzyme A is a weak point. All right, let's focus on enhancing the enzymatic activity at this point. Professor Kamada, how can we increase the expression level of the enzyme?
Try adjusting the gene sequence. Let's take a look at the sequence. Here's how I would do it. This should increase the enzyme levels. That is an impressive increase.
Let's commercialize this right away.
By using the genome sequence to design biosynthetic pathways, modulating intracellular processes, and harnessing gene expression, we can enhance the productivity of microorganisms as biomanufacturing engines. Our new, highly productive business will manufacture high-performance SMART cells in ways that are more cost-effective and energy efficient than ever before.